Hello class, in this video we'll explore what is NMR spectroscopy, how it works, and how to analyze the spectroscopic data from this technique. This is going to be a lengthy video as there is a lot of things to unpack and is often the most challenging thing to understand amongst the different spectroscopic techniques. Nuclear magnetic resonance spectroscopy, or NMR spectroscopy for short, uses radio waves to obtain information about the structure and connectivity of atoms in a molecule. In particular, it enables us to determine the number of hydrogen and carbon environments present, which is incredibly useful to distinguishing between structural isomers. Let's unpack how NMR spectroscopy works. This can be quite technical, confusing, and abstract, but it's a VCAL requirement for you to understand the principles of NMR spectroscopy. The first thing I need you to understand is that a substance can only interact with radio waves if the nuclei of the atoms have a property called nuclear spin. This is a property that is possessed by nuclei of an odd mass number. Two primary examples of this is hydrogen-1 and carbon-13. The nuclei of hydrogen-1 or carbon-13 spins around an axis which generates a magnetic field. In the absence of a magnetic field, the spinning nuclei are randomly orientated, but when an external magnetic field is applied, majority of the spins will align in the same direction which has a lower energy. Alternatively, some of the nuclei will have higher energies and will therefore spin in the opposite direction of the external magnetic field. This is best represented by the following animation. So how does this involve spectroscopy? When we radiate the sample with radio waves, the sample will absorb radio waves of certain frequencies, which causes a nuclei to flip into a higher energy spin state. Shortly after, the nuclei flips back into its low energy spin state and releases the absorbed energy, which can be measured and represented on an NMR spectrum down below. The amount of energy that is emitted will depend on the chemical environment of that nucleus, and this is compared to the nuclei in tetramethylsilane, or TMS for short, which has the following symmetrical tetrahedral structure on the right hand side. When we're talking about the chemical environment of a nucleus, we're referring to the group of atoms and electrons that surround it. It is an important skill to recognize the number of hydrogen and carbon environments that are present in a molecule. To do this, we need to consider the connectivity and the arrangement of atoms that's surrounding the nucleus and whether there's a plane of symmetry. Let's look at a few examples. Ethane is a symmetrical molecule. This means that the following 6 hydrogens are equivalent and will absorb and emit radio waves of the same frequency. Therefore, this has one hydrogen environment. Similarly, the 2 carbons in the molecules are also identical in the sense where they are both attached to the same group of atoms. Hence, there's also one carbon environment. Propane is another symmetrical molecule. As a result, the following 6 highlighted hydrogens are equivalent. However, the 2 hydrogens at the center will absorb radio waves of a different frequency as it has different connectivities. Therefore, propane has 2 unique hydrogen environments. If we examine the carbons, the 2 carbons on both ends are identical due to symmetry, and the carbon in the center contains different atoms. Therefore, there's also 2 carbon environments. If we inspect butanone, we can see that there's no plane of symmetry. As a result, these 3 hydrogens are different from these 2 hydrogens as well as the other hydrogens found on the other end. Hence, there are 3 unique hydrogen environments. Following the same logic, each carbon is connected to different atoms, hence there are 4 unique carbon environments in butanone. Although I have yet to fully explain the principles of NMR spectroscopy, I want you to see if you can identify the number of carbon and hydrogen environments in the following molecules. Pause the video now and resume again when you've got an answer. The first molecule on the left is asymmetric, and we can see that there are 2 carbon and 2 hydrogen environments. In the second molecule, there is a plane of symmetry. Therefore, these hydrogens are equivalent to each other, and so are these hydrogens. Hence, there are 2 unique hydrogen environments. Similarly, these carbons are identical to each other as well as these, and together with the carbon from the carbonyl group, there are 3 unique carbon environments. You should be able to readily identify that the third molecule contains 3 hydrogen environments and 3 carbon environments. The last molecule contains a plane of symmetry. Hence, there are 3 hydrogen and 3 carbon environments. Have a go with the last 2 examples. Pause the video now and then have a go. The following ester has no symmetry whatsoever, so there are 2 hydrogen environments and 3 carbon environments. On the other hand, this ketone is symmetrical, So there are 3 hydrogen environments and 4 carbon environments. We said earlier in the video that each hydrogen or carbon environment in the sample will emit radio waves of specific energies that's relative to the TMS. On the NMR spectrum, the difference between a signal and the signal produced from the TMS is referred to as the chemical shift, and this is measured in parts per million. As shown in the NMR spectrum below, the TMS produces a single peak at 0 parts per million. Sometimes, we often denote the chemical shift by using the Greek letter delta. Now that we know what chemical environments, chemical shifts, and what an NMR spectrum looks like, we can soon begin to learn how to analyze the spectrum. To do this, we often need to analyze 4 key things, one of them being the number of signals produced, which correlates to the number of unique hydrogen or carbon environments. We also look at the magnitude of the chemical shifts of each signal, the relative area under each signal, and lastly, the splitting patterns for each signal. Collectively, we use this information to then work out which hydrogen or carbon in the following molecule is responsible for the following signals on the NMR spectrum. The first form of NMR that we'll be looking at is HNMR. HNMR or proton NMR has 2 specific types, low res and high res, and they both give information on the number of hydrogen environments in the analyzed sample. The amount of signals on the spectrum will tell us how many unique hydrogen environments are present, and the hydrogen environments that belong in the same chemical shift are said or described to be equivalent and form a single peak with the same chemical shift. Let's use ethanol as an example. If we were to predict the number of hydrogen environments present, we should expect 3 hydrogen environments. The following low-resolution HNMR spectrum of ethanol also displays 3 signals, which is consistent with our prediction. I would like to add that hydrogens that are closer to an electronegative element, such as oxygen, tend to have higher chemical shifts. The NMR spectrum will also tell us the area under each peak. The area under the peak of each signal tells us the number of hydrogens in that environment as a ratio. Using the exact same example, we can see that the ratio is 1 to 2 to 3. What this suggests is that we know that there is 1 hydrogen in this particular environment, 2 hydrogens in this environment, and 3 hydrogens in this environment. Hence, we can deduce that the first signal is caused by the OH, the second signal is caused by the CH2, and the third signal is caused by the methyl group. We can also determine the identity of the hydrogen environments by comparing the chemical shifts of each of these signals to those found on the data booklet. This means that if you've got a signal with a chemical shift of 0.9 to 1 parts per million, there's a good chance that this is caused by the hydrogens found in the methyl group. Please note that these values can change depending on the solvent that it's being used. As I've stated earlier, you'll find that hydrogens that are closer to an oxygen will have a higher chemical shift. To work out what hydrogen environment is responsible for each signal in the HNMR spectrum, I don't really refer to the data booklet as my primary method, as I often look at other things such as its splitting patterns or the area under the peaks. After I've done that, I then use the data booklet as a backup tool to help then verify. Let's now look at high-resolution HNMR spectroscopy. A high-resolution spectrum contains the exact same information as a low-resolution spectrum, but each signal in the low-resolution spectrum appears to have been split into several peaks. The number of splits in a signal corresponds to the number of non-equivalent hydrogen atoms that are found on the neighboring carbon atom. We can predict the splitting pattern by using the n+1 rule, where n is the number of neighboring hydrogens in non-equivalent hydrogen environments. The following image over here shows the differences between a low-resolution HNMR versus a high-resolution HNMR for the same compound, and you can see that the high-res again shows you different splitting patterns. We call a splitting pattern a multiplet and give it certain names depending on the number of peaks it splits into. So you can either have a singlet, doublet, triplet, or a quartet. An example for each is shown below, where the highlighted hydrogen shows you which hydrogen is responsible for the following splitting pattern. Let's look at the doublet. These hydrogens over here have 1 neighboring hydrogen atom, and because it has 1 neighboring hydrogen atom, this is why it causes a doublet, because 1 + 1 gives you 2. If we look at this example over here, these hydrogens have now 2 neighboring hydrogens that are found on the adjacent carbon, which is why it causes 3, because 2 + 1 gives you 3 using the n+1 rule, and we could use the same logic again for the quartet. Let's now look at some legitimate examples using high resolution HNMR spectroscopy. On this slide, I've got a high resolution HNMR spectrum of ethanol. By now, you should be able to see that there are 3 unique hydrogen environments, and therefore, which is why you've got 3 signals. Because we are given the areas for each of these signals over here, I can tell that the hydrogen on the hydroxyl group causes the signal on the left, the hydrogens in the CH2 group causes the peak in the middle, and the hydrogens in the methyl group causes the signal on the right hand side. However, to further verify this, we could also use our understanding of how splitting works. Let's use CH3 as an example. The hydrogens in the methyl group have 2 hydrogens in the neighboring carbon atom, as you can see here. Using the n+1 rule, we know that this CH3 signal is therefore going to produce a triplet because 2 plus 1 gives you 3. Similarly, the hydrogens in the CH2 group have 3 hydrogens in the neighboring adjacent carbon. Again, using the n+1 rule, 3 plus 1 gives you 4, so therefore this signal is going to produce a quartet, and again this is illustrated down below in the HNMR spectrum. Because this hydrogen on the hydroxyl group doesn't have a carbon directly attached to it, this hydrogen will not undergo any splitting whatsoever, which is why it just produces a singlet. Let's now look at another example. In this example, we know that there are 3 unique hydrogen environments, hence the 3 signals. Using the area under each peak, I know that the CH2 is going to be responsible for the peak shown on the left hand side. To identify which one of these methyl groups is responsible for the following signals, I'm going to be analyzing a splitting pattern. Let's analyze the CH3 group that's found on the left hand side. The hydrogens in this methyl group has 2 hydrogens in the neighboring adjacent carbon. Therefore, using the n+1 rule, it's going to therefore produce a triplet. Therefore, the hydrogens in this methyl group belongs to the peak shown on the right hand side. If we are going to be looking at the hydrogens that's found in this methyl group, notice that there are no hydrogens that's found on the neighboring carbon atom. And as a result of this, this is going to produce a singlet using the n+1 rule. In the last example, we are given the HNMR spectrum of a compound with a molecular formula of C2H4Cl2. The question wants us to identify this compound. If we look at the HNMR spectrum down below, we can see that there are 2 signals, which tells us there are 2 hydrogen environments. Because we are given the ratio for each signal, I know that there's going to be 1 hydrogen that's responsible for the left peak and 3 hydrogens that's responsible for the peak on the right hand side. With this information alone, I could probably deduce the identity of this compound, but I'm also going to take into consideration of its splitting pattern. Based on the splitting pattern, we can see that there's a quartet and a doublet. In order for us to produce a quartet, this particular signal must have 3 hydrogens on the adjacent carbon atom, and the doublet is caused by 1 hydrogen that's found on the adjacent carbon atom. So therefore, this is what's causing these peaks, and therefore using a trial and error approach and using the information that we've collected, I know that this compound is going to be 1,1-dichloroethane. We've now covered the theory behind HNMR spectroscopy. Thank you for watching this video, and I'll hope to see you guys again in the next one. Bye.